We're going to get started on this. What do you notice taking a look at those two expressions? What do you notice in one of them? What do you notice in the other? Can we come up with a pattern? It doesn't have any instructions about what you do. What do you think you might do in this case? That's a really hard question because, like, who knows what the point is? But anybody have anything they want to? This is it. To me, this is really important. Is we grow very attached to the instructions of a question telling us what we're supposed to do. We have all these tools in our tool belt, and as long as somebody tells me which one I'm supposed to use, I can do it. But that's not real life. That's not real math. That's not really the way things work, right? To be more versatile, to really get to a point where we're doing stuff on our own, we should just have a question and we have to figure out what to do, right? You get a little bit of that here and there. In the analytic geometry unit in grade 10, you get a little bit of that. Anybody see anything about them here? Yeah, that's you.
I did the b squared minus 4ac both of them, and I got a negative 3.
Interesting. I love this. So the trinomial at the end, right? Is that what you're talking about? The second part? So check the discriminant. They're both negative. We hopefully know what that means. Very interesting. Okay. Anything else?
The coefficient on the x term in the trinomials is the negative of the constant in linear. The constant in the square constant.
Okay, here we go. So what you're saying is there's a +2 here and a -2 here, and a -3 here and a +3 here. So the same number but switched signs. And what did you say about 4? It's the square, the 9, okay? There's one more little thing that's really important to notice, those details right there. One other thing on that same note. Okay, I want you to expand both of those. Go. Okay, did you get the same first line as me? A lot of you went one step further. Very good. A lot of people got the same. So what happens at this line? Who can tell me what happens here? A lot of you did it. So, but what happens? Can you describe? It's a difference of cubes. And that happens because I have a positive 2x squared and a negative 2x squared and a positive 4x and a negative 4x. Like, these terms cancel. Just like a difference of squares, but these are both cubes. X cubed minus 8, right? X cubed is a perfect cube. 8 is a perfect cube. It's 2 cubed. Very nice. Next one. Try expand that one. So same idea. We get x cubed, except this one's plus, 27. What would we call that? A sum of cubes? If we're relating this to what we already know from grade 10, a difference of squares, but there is no sum of squares, what's the common mistake? Oh my goodness. X, when you're factoring, people do this. X squared plus 16 is x plus 4 all squared. So this is like a sum of squares, but that is not true. Why is that not true? Because if I expand x plus 4 times x plus 4, I actually get x squared plus 8x plus 16, right? So that's not the factor form because it's not equivalent. It's not the same thing. When you expand, you don't get that, right? So there is no such thing as a sum of squares in terms of factoring. You can write it, but you can't factor it. You can't do anything with it. But it turns out difference of cubes and sum of cubes will both work. So there's one more little thing that we might have missed, or maybe it didn't seem obvious at the time because it didn't seem relevant. We noticed that those two have a relationship of one is the square of the other. So the last term is the square of the second term in the first, and it's the same here, right? Those are squared. Like x squared, it's not a coincidence, it's this term squared. So if that first term was something else, this would be something else. That makes sense? So if we do the same thing here, you can just watch for a minute. A times a squared is a cubed. A times ab is plus a squared b. A times b squared is plus ab squared. And then I get negative a squared b. I'm multiplying these ones now, right? And I get negative ab squared minus b cubed. So I notice that a squared b and a squared b and ab squared and ab squared have opposite signs. And why is it important to do it this way? This is the general case. We're going to use it backwards today, right? It's not often, I don't think, where you'd have that and you'd have to expand it. And this is a trick to quickly expand it. That's not the point today. The point is if you have a difference of cubes, I can factor it back to that first step. But factoring often is useful thinking about the expansion. So that's why we're just looking for patterns in the expanding of something, but we're going to use it to work backwards to factor a difference of cubes and a sum of cubes. Today, that's what we're doing. But this is the general form. So we have to note, like this is basically a formula. We have to notice, we have to memorize the formula that this is the cube root of that. This is the cube root of that. And then I've got the first term squared, the last term squared, and the first term times the last term. Whatever they are, because we used A's and B's for the general term, for the general form. So whatever A is, whatever B is, you multiply them together. That's what you're noticing about this, right? And because this was just A, this is A squared. A could be anything. It could be 2x. So then it'd be 2x squared, right? 2x all squared. Okay, and then for this one, same idea. A times A squared is A cubed minus A squared B plus A B squared plus A squared B minus AB squared plus B cubed. So I get the same thing. Those are same opposite signs, and I'm left with A cubed plus B cubed. So formula to factor back that direction. Okay? Any questions? That's basically it for today. We're going to do a few examples, but you need to know the formula. Ooh, that's an easy one because we kind of just did it. That's okay. Let's actually see it in action, go in the other direction. So then how do I actually use this formula? This is how I would do it, right? If you memorize the formula, then you're just plugging in values, but you take the cube root of the first term. Cube root of x cubed is x. Cube roots are very different from square roots. You'll notice this as we start to get into this more and more and more. Cube roots, you don't do a plus minus. You've seen this before, I'm sure, but you got to really remember this. When I do a square root of something or a fourth root of something, we've got two possible answers, plus minus. Cube roots, any odd, it's not the same. Why is that? I'm just going to scribble this for a minute, because negative 2 all squared is 4, and positive 2 squared is 4. So when I go in reverse, I don't know which one I started with. Whereas negative 2 all cubed is negative 8, and positive 2 all cubed is positive 8. Like, they're different. So when I do the reverse, I get that value. And this ties into a lot. I don't know if we've talked much about this. I think I mentioned it, but you may not have talked much about it in grade 11 or grade 10. This right here, that ties into the importance of what is a function. What makes a function so special? Why do we talk about functions? Why do we have a different notation, function notation? Why is something failing the vertical line test? Why does that matter? This won't really be important for what we're doing today, but just as a general kind of interest thing, bigger picture stuff. Why? Because when we're doing mathematics, it's really important if when I put in an input, I get a unique output or I don't. I want to know that. And in special cases where you do, like this, okay, that's better, basically, because I know I've got the only value. Whereas when I do it like this, and I get two possible values, that's not as useful. It's not as strong, not as powerful. Anyway, so that's kind of why we talk about functions the way we talk about them. So the cube root of x cubed is x. The cube root of 8 is 2. And this is something you need to memorize, but if we go back up and look, the first bracket shares the sign. People will mix that up. They'll get that backwards, right? To me, that's a big part of the memory work. You see it when you're expanding how it works out, but when you factor, you kind of just have to memorize it. So that one's negative. And then how do I get the next bracket? I square the first thing. I square the last thing. And then the middle thing is the first thing times the last thing. So 2 times x, and that has the opposite sign from my first bracket. Those signs are opposite always. Does that make sense? We're done. That's it. Factored, you're done. Something a little bit trickier. So what do we notice about this one? There's 2 variables, very good. There's more coefficients. This is maybe what's trickier about sums and differences of cubes compared to the difference of squares, is we know our perfect squares fairly well. We don't recognize perfect cubes as well. How many people knew that 343 was a cube, was a perfect cube? Some people might, good, but a lot of people might not. But if you see 2 terms, some are different, and a lot of other things are cubed in there, you're probably looking at a sum or difference of cubes, and you check the rest of them and see what happens.
Is it safe to assume that in this class that everything's going to be, you can actually the cube root? Like if you give us a number, will it actually divide it properly or not?
No, I would check it on my calculator. You're going to have to figure it out anyway, so I would check it. Unlikely that I would give you one where everything works except for one part, just because that's kind of like what do we gain out of that? But certainly there will be times, we'll see it more in the next unit, where that doesn't work out that way, but we'll talk about how to deal with that. Okay, so what is the cube root of 27? X cubed. 3x. What's the cube root of 343? 7. So this part's going to be 7y, and they share the same sign. Okay. So I square the first one, that becomes 9x. I square the last one, that becomes 9x squared, sorry. Square the last one, 49y squared. And then the middle term is the first times the second, and it's got the opposite sign, so it's going to be minus 21xy. And the last one's always positive. Formula, right? But how do you remember the formula? That's how I remember it. I get the first bracket, square the first, multiply them together, square the second, memorize the way the patterns of the signs go. And you can always expand to check your answer, right? How would I do that? I would do something like, this is positive 27x squared. Sorry, no, that's not right. 3 times 21, I'm going to have work that out. So 63x squared y, and then this is also 63x squared y, and they have different signs, so they cancel out. It's a little bit, like, it's not as obvious. You have to really think about it. It's not an easy check. You got to do some mental math, but yeah.
I'm just wondering, are you going to put the scanned copy of this note online?
Yeah.
Because I realized you weren't recording this.
Yes, definitely. Yeah. Okay. Next one. We just have a few more examples, and they all just are a little bit different. What do we notice about this one? I notice there's 2 terms. X to the 6. What do we notice about that? It's even. Good. What else? Nice. I like that. That's a really good point, because we're not talking about functions or any of that stuff we did in the first half of this unit, but that was really important for the first 3 or 4 days of this unit, was the function even or odd. So this is an even function. If you were asked something about it and it's an even function, very interesting. Yeah, that's good. So it's not x cubed, but can I take the cube root of x to the 6? John thinks yes. What is it? X squared. Nice. X squared all cubed is x to the 6. So x cubed, x to the 6, x to the 9th, x to the 12, any multiple of 3 in an exponent will work for this purpose, right? So I would be like, oh, gee, is 729 a perfect cube? I wonder. Is it? Somebody checked it? What is it? 9. So let's go ahead and do that. So the cube root of x to the 6 is x squared. Oh dear. X squared, and the cube root of 729 is 9, and it's the same sign. Oops, something interesting just happened there. Square the first term. Square the last term, and it's always positive. And the middle is the first times the last, and it's got the opposite sign, so it's plus 9x squared. And again, you could expand that if you want to check that. If you think, oh, maybe it's different when you play around with the exponents. But when we did the general form of this, the formula, and checked it, I mean, it's going to work for anything you plug in there. So I can plug x squared in for a in that formula. It's going to work. It has to. But convince yourself, check it, absolutely. What did we know? What happened here? Yeah, so do we have to keep going? Of course. The whole point is factor fully. Like, the whole point is how much can we notice, what can we do? So this is x plus 3, x minus 3. Can I factor this further? No. What's happening here? Factoring is all about what you notice. Factoring is so much like an art, and we saw this a little bit on Friday, is that if you notice important things, it makes your life so much easier, right? There was a couple of little tricks where we were able to factor way faster in 2 little easy steps compared to doing like a big synthetic division. So if we notice things, sometimes we have to, sometimes we don't, but it just makes our life easier. But factoring is so much about patterns and what you notice. Elif. So we've got a common factor here, always common factor first. Sometimes that makes the rest of the question doable. And sometimes it just makes it easier. Could I factor this? Could I have factored any of these with factor theorem? See, now we're thinking. Let's go back up to, let's go to this one. Could we have used factor theorem? What is factor theorem? That's how we've been factoring for a few days. So you'd be checking values, right? Check 1, check -1. Check 2, check -2.
Yeah, I think you could get the -2 works.
Yeah.
You can set that in and then divide it.
Right. If I put 2, good. If I put 2 in, this is going to be 0. So x minus 2, I'm going to find that as a factor. That's going to work. That should be fairly obvious looking at it. Why wouldn't synthetic division work? I mean, here's a tip. Without even seeing it, you could say, of course it's going to work. It's math. It's like it always works. That's how math is, right? It's not like there's no exception for factor theorem, except factor theorem works except when you have a difference of cubes. No, right? Of course it's going to work. Factor theorem is, we're finding factors. Synthetic division will work. You can always divide. You'll always get the result. Go ahead and try it if you're not convinced. Of course it will work. But this was so much easier. Right? So much easier than using factor theorem. Where are we? So I could, the whole point of talking about that is I could have used factor theorem on that had I not noticed there was a common factor, which I think everybody would, but had I not noticed that, I guess I would have been doing factor theorem and putting in all those ghost terms, those placeholder terms, right? But it would have been a lot longer than this. So this ends up being 8a cubed plus 125. Okay, go ahead and factor that on your own. So we see that's a sum of cubes, right? 125 is 5 cubed. If you haven't already, go ahead and factor that. Okay, everybody okay with that? How many do we have more? 4 more to go here. What's going on here?
The terms are squared instead of actually.
Terms are squared, very good. Jason, what were you going to say? Same idea. Is this a difference of cubes? No, because there's no cubes. So this is a little bit different from what we were just doing. But you probably saw questions like this in grade 10, maybe a little bit in grade 11. They're hard in grade 10. We're going to revisit them. And first of all, see how much easier they are now. Give ourselves a little pat on the back for how far we've come since grade 10. It's kind of nice. Our algebra skills are better. The things that we notice about algebra, the way we look at these things is better. This is like x squared, or I'm going to use a different, a squared minus b squared. But a is x minus 4 and b is x plus 1, right? But it's still the same idea. That's a hard thing to wrap your head around when you first start doing it. X squared is just something squared. Like that's what a variable is. A variable stands for something, anything. That thing can be a polynomial expression. Can be a polynomial, right? Could be anything. But we do a little bit of this in grade 10. And so I could use this same logic on anything we do in grade 12 as well. Like this could have been a cube question. It would have been pretty complicated, but so what does this mean? It means I'm going to use big square brackets. I get something plus something times something, the same something minus the same something. And that's the square root of the first term, and the square root of the second term, and the square root of the first term, and the square root of the second term. If you don't quite see that, I would encourage you, again, to go back, like do a question where it's just normal. X squared minus 9 is x plus 3, x minus 3. And think about it that way. Yep. Oh, thanks. Minus should be minus. And are we done? We're not done. We have to simplify this. Don't stop there. Don't expand in the end, because the whole point is factor, but we certainly want to simplify what's in the brackets. So this is x minus 4 plus x plus 1, so that's going to be 2x minus 3. And x minus 4, I'm going to do this in 2 steps, but if you could do this in your head, you could do it in 1. This is like this negative is going to be distributed. Some people miss that, so it's a really simple little thing, but be careful. 2x minus 3. So x minus x is gone, and this actually ends up being negative 4 minus 1, which is negative 5. Don't expand. The factor fully, that's the factored part. The negative 5 is like a common factor, right? We would pull that out, so we want to keep it out. Okay, any questions about that? Let's try the next one, F. It's a little reminder, like these are little tidbits of reminders of some of the more challenging ways that we know how to factor. Do we know how to factor fractions? We haven't seen this yet this year really, but do we know how to do that? I hope we remember. Again, this looks like a difference of squares, but if you're not sure because you're not sure about the fractions and stuff, then you have to come up with a way that you could convince yourself whether it is or it isn't. But to me, how would I recognize this as a difference of squares? Well, it's got an x squared, it's got a difference, it's got 2 terms, and all those numbers are perfect squares. So it kind of looks like it probably might be a difference of squares, right? But if we think about fraction multiplication, 4 over 5 times 4 over 5 is 4 times 4 over 5 times 5, 4 squared over 5 squared. And this was 4 over 5 all squared, right? So how do you square fractions? Square the top, square the bottom. Quick little reminder. Same thing for cubes for any exponent. So this is like x over 3 plus 4 over 5, x over 3 minus 4 over 5. Just take the square root of everything. Is that okay? Two more. Everybody's favorite. This one's easy. X plus 7 squared, right? Yeah? Good? Everybody like that? Right? It's an easy one. No? What did I do wrong? Is it? How would we know? X minus, let's find out. How would I, what if I had one of those ones that like, oh, Ms. Belair said something about this and I don't remember. My grade 10 teacher said something about this and I don't remember. How would we check? Okay, good. Stop there because you want to say something else, don't you? I'm just going to do it. Don't do it. Just watch. X times x is x squared. x times negative 7x, negative 7x plus 49. So I got the plus 49, I got the x squared. That's not 0. That's negative 14, didn't work. The only time this works, convince yourself. Don't take my word for it, because you'll forget. Convince yourself, is when the signs are different, because I get x squared minus 7x plus 7x minus 49. The only time it works is when the signs are different, and if the signs are different, that's going to be a negative. So Emma, go ahead. What were you going to say? Yeah, this is not factorable. I would say with pretty much certainty, the only time you're ever going to get a question on a factoring test that's not factorable is one like that that's obviously not factorable. Now that we're in grade 12, things will come up that aren't factorable. We've already seen it in trig, where we use the discriminant to determine that it's not factorable, and we can say, or we get, factors that don't work because of what we're doing, like in trig. Like that happens now in grade 12 more, but I'm not trying to get you. I'm not trying to trick you on a test, or like as teachers, we're not trying to do that. So, maybe a question like that to make sure that you know the difference between a sum of squares and a sum of cubes. Sum of cubes is factorable, sum of squares is not. But really, that's a grade 10 question. I don't foresee it being on the test. It's possible, but like, usually that's the kind that you might get that's not factorable. So if there's, I don't know, 6 to 10 factoring questions on 10 would be a lot, I think, but 6 to 10 factoring questions on the test, and you say 4 of them aren't factorable, you're probably wrong. Okay, maybe there's one, there's probably none kind of thing. Okay, and if it's not factorable, it's not factorable for a reason like that. Okay, last one. I want you to give this one a try. This is like that other one that we did, where this is, I'll give you a hint, it is like just factoring a regular quadratic, except that the thing that I'm squaring, it's not x squared plus 4x minus 21. It's like a polynomial, right? Or a binomial in this case. A binomial squared plus 4 times the same binomial. That's really important, minus 21. So try to do it. In grade 10, you could totally get away, and you still could, quite frankly, but with expanding that. If I expanded this, and I got some trinomial result after I collected all my like terms, and then factor that, I'm going to get the same answer. But you're going to be better off in the long run if you can get yourself to be able to factor this the way it is, because you start just being stronger with your algebra in general. Okay, so challenge yourself. So give it a try. I'm going to help you a little bit along the way, so you could start with that. And if you're not sure, this definitely is a simple trinomial. You're just looking for 2 numbers that multiply to 21 and add to 4, and you're going to put those 2 numbers there. So if you haven't done it yet, you could start with that. It shouldn't take you long, so I'm going to give you about 10 seconds. So who knows what those numbers are? What are those 2 numbers? 7, so positive 7 and negative 3. 7 times negative 3 is negative 21. Positive 7 minus 3 is positive 4. Love it. And then you ask yourself, what do I put here that's going to make all this work? Right, x plus 3 in both cases. You might have done something where you like, let x plus 3 be a, or a be x plus 3, and do a squared plus 4a minus 21, and then sub it back in. But my goodness, like, and you could do that. You could just expand and simplify and factor that. But again, challenge you to, let's try to push ourselves to go a little bit further. And then I certainly simplify these. So this is x plus 10 times just x. Doesn't always work out that way. That one happened to. Any questions?
All you need one, you can get started. Don't take one from your other teacher.